Good morning, everyone. For the next session, this is lecture 6. It is started by springs. So, in previous week, we have seen torsion and other things. This week, we are going to see about springs. Springs are elastic body which absorb energy due to resilience. The absorbed energy may be released as when it is required. The spring, which is capable of absorbing great amount of energy for the given stress without getting permanently deformed, it is known as the best spring. So, if you give any force, it will get deformed and it will stretch at a very huge displacement, and again it will come to its original position. It is called as a best spring. There are two types of springs. One is laminated or leaf spring, another one is called as helical spring. So this type is called as a leaf spring. So it consists of a parallel of metal sheets combined with each other at the center, and it will be in a circular curved path. So it will be supported at the two ends and the force will be applied here. So it will start to displace in the vertical direction. So when it moves up, again it will bring down. So these type of springs are used in heavy vehicles such as lorries, buses, etc. So let's see about this. So consider this diagram as a leaf spring. Here total weight is acted as W and the total deformation is going to be delta. So the span length is L and the weight is evenly distributed on both the sides. So here W by 2, here W by 2. So total weight is W and thickness of the plate is T. Sigma is the maximum bending stress developed in the plate, and N is the number of plates and L is the span of the spring. Then B is the width of the plate. Here delta is the original deflection of the top spring. So let's start with the expression for maximum bending stress developed in the plate. The load W is acting at the center and it is nothing more or less a simply supported beam. You can see that it is a beam of length L with a 2 support and a central point load. So this is the case. So bending moment at the center, it will be load of one end into L by 2. That is, you have to find out the moment about the center point, which means that W by 2 into half of the L, that is L by 2, that will be moment. So W by 2 into L by 2, which is equal to WL by 4. Then moment of inertia about the plate. So about this point, you have to find out the moment of inertia. You can see that the thickness of the plate is T and the width is nothing but it is perpendicular to this screen. You can assume that the width is nothing but the distance that is perpendicular from the screen. So B cubed by 12. So here D is nothing but the thickness of the plate. So B into P cubed by 12 will be moment of inertia I. So next, the bending relationship is M by I equal to sigma by Y. So we have to find out the sigma value. Here Y is nothing but, usually we will take D by 2. Here D is nothing but your thickness T. So T would be T by Y is equal to T by 2. Moment you know that you have already found out it is W L by 4 and I value is B T cubed by 12. Substituting everything and find out the sigma value. But before finding out, you have to see that this moment value. So simplifying this, you are putting the moment on one side. You can simplify that it is for one plate, but you have n number of plates. You have n number of plates. So multiplying that, so n into m will be equal to n into sigma bt square by 6 after simplifying this. So substituting moment value, that is WL by 4 into here n will come here. Sorry, n into m is equal to WL by 4 because this moment is taken for the whole number of plates, for all the number of plates. So it is equal to n into sigma bt square by 6. Rearranging this, sigma is equal to 6 WL by 4 and bt square. So simplify again, 3 by 2 WL by n bt square. So this is the formula to find out the bending stress, that is maximum bending stress. This is the first derivation. Second one, expression for central deflection of the leaf spring. So assuming that this is a leaf spring, which is in a circular path which has a center of O and radius capital R. So here it will be total radius and this distance is delta. So DOC distance will be R minus delta, and this is L by 2 and this is L by 2. Now consider this particular triangle AOC. Here the distance AO is radius and AC is L by 2 and OC is R minus delta. So in this diagram we know that by Pythagoras theorem AO square is equal to AC square plus CO square. So substituting those values, R square is equal to L by 2 whole square plus R minus delta the whole square. Expanding this, L square by 4 plus R square plus B square minus 2RB. So in this case delta is already very much lower value, so we can neglect delta square which will be much smaller value. So neglecting delta square, so balances L square by 4 plus R square minus 2RB. So rearranging this, 2R delta is equal to L square by 4. So delta is equal to L square by 4 into 2R, L square by 8R. So this is then equation, that is how much delta it will be there, delta for things. Then, but the relationship between bending stress and the modulus of elasticity. By this relation you already know that sigma by y equal to E by R. Sigma by y equal to E by R. So radius is equal to, rearranging this, radius is equal to ET by 2 sigma. Here y is nothing but T by 2. Y is T by 2. So substituting this value in delta, you will get delta is equal to sigma L square by 4 ET. Sigma L square by 4 ET. So this is the maximum deflection of the spring. So these are the derivations you have to remember for the leaf spring. Let's see with a small problem. A leaf spring carries a central load of 3000 Newton. The leaf spring is to be made of 10 steel plates 5 cm width and 6 mm thick. If the bending stress is limited to 150 Newton per mm square, determine the length of the spring, deflection of the spring at the center. So take E equal to 2 into 10 power 5 Newton per mm square. You can see that central load is 3000 Newton. Number of plates is, there is N value is 10. Width of the plate is B, 50 mm. Thickness is 6 mm. Bending stress is 150 Newton per mm square. And E value, modulus of elasticity, 2 into 10 power 5 Newton per mm square. So first we have to find out the length of the spring. So for that it is given that the sigma value is already given. So first substitute the sigma formula, that is bending stress formula, and you have to find out the value of L. So you can substitute all the other things and find the value of L, which is equal to 600 mm. And then after finding the L, you have to find out the deflection value. So then substitute in the delta formula and you can find out the maximum delta at the center, that is 11.25. Then next type problem is laminated spring 1 meter long is made up of plates of 5 cm wide and 1 cm thick. If the bending stress of the plate is limited to 100 Newton per mm square, how many plates would be required to enable the spring to carry the central point load of 2 kN if E equal to 2.1 into 10 power 5 Newton per mm square, and what is the deflection under the load? You can see that laminate plate which is the length of 1 meter. Here length is given. They have asked how many number of plates would be required to enable for 2 kilonewtons. So they are asking N value. So N is not given here. So same here, given data are given. Then as usual the first sigma formula. Here N is unknown. You don't know the N value. So with this substitute all other values and find out the N value. So N here is 6. So 6 plates is required. Then delta is also required. So delta formula is substituted and find out the delta value. So this is the problem for laminated springs, or it is called as leaf springs. So with this lecture gets over. Thank you.